if there are no, oh, I guess, is this working now? Should I use this? This good? No?
If you
Sorry?
tap on it,
Is that better?
yeah, this one's fine.
Okay. So I guess, yeah, assuming you said, if there are any burning questions left over from last time, we can start with those. And if not, yeah, no. If not, then, no, none.
Well, maybe I can, you already answered it, but maybe I can ask a question in case somebody else had the same. You use the word thermal state to describe the state of the reduced density matrix, but you meant that it is just a mixed state and not necessarily.
If I did, I misspoke. I should have said Gaussian state. That's the crucial thing that makes everything work. So, if you remember the expression in the reduced density matrix, it's not the absolute most general Gaussian density matrix you can write down, but it's a quite general one. And then in a separate calculation in which thermal density matrix played a role along the way as a tool, we found the entropy of a general Gaussian density matrix of that particular form that came out of tracing out half the oscillators, some subset of the oscillators, and then applied that to rewrite the entanglement entropy in terms of the original, in terms of the original parameters of the system that we started with. So the logic was, here's a bunch of oscillators divided into two. They're interacting in some linear way and in some quadratic way, so that it constitutes one big harmonic oscillator, so to speak, in any dimension. And take a subset of those, take the ground state as a whole thing, trace out the subset, you get an effective density matrix for the remainder. The ground state itself is Gaussian, of course. The ground state of a harmonic oscillator, the wave function always looks like a Gaussian as a wave function, and then the density matrix made from it is just the product of the two the wave function with its complex conjugate, so that's also a Gaussian. Tracing out is just doing some sort of integral over some of the variables of that Gaussian. So whenever you integrate a Gaussian, you get another Gaussian. And so we had a Gaussian, the description of the subset, the remaining set of, the subset of interest, so to speak, of the oscillators. That was described now by a mixed state, but it was still a Gaussian wave function. And then we set that aside for a little bit. We went over and said, just as a mathematical exercise, what is the trace rho log rho entropy of a Gaussian density matrix at that form? And then we took that general result, went back to the specific Gaussian that came out of the tracing out of the, from this coupled oscillator system, and expressed the general answer in terms of the mass matrix or the kinetic energy matrix and potential energy matrix for that set of oscillators, that combined set of oscillators. So the answer, well, we won't be using it for a little while, but the answer I remind you was we defined some operator which was using WA alpha and W alpha beta, and the entropy of that, and then it has a set of eigenvalues. I don't think I gave them a label, but let's call them lambda n.
That must with B, right?
Sorry?
Instead of bigger,
Oh, this should be a B. Yeah, that's crucial, right? Yeah. That should be a B.
So projector
Sorry?
is a rank.
Huh? I
And
didn't
this
sorry.
actually looks like a. Is it a projector or is a rank less than the rank of the A's?
In general,
Less. Number of alphas less than number of A's.
in general, it will be less.
Yes.
You can get zero eigenvalues. You can get zero eigenvalues. In general, I'm not sure. In practice, maybe it's rare to get, but there's nothing in principle stopping this from being some zero. In fact, well, there's a sort of trivial case where it's all zero, which is, it happens because this whole, there's a trivial case where it's all zero because these off diagonal, if you happen to choose two sets of, if in your original set of harmonic oscillators there were no springs joining these oscillators to these oscillators, then this off diagonal thing would be zero.
Is W a
I was going to write the word W was the square root of V relative to, or with respect to G. And I have to remind you, I suppose, what G and so on were. So the original set of oscillators had Q dot and Q dot. So V was the the potential energy matrix of a set of springs coupling the oscillators together, and G was the mass matrix, kinetic energy matrix, and then W, this is the full W, right? So if I give it its indices, W, so at the level of the whole system, W was the square root of V. What this means, when I write it like this, I mean think of G as a metric, and then that allows you to raise and lower indices, and by definition, this is what GAC, this is a big C, let's say, GAD, GD. So, no, not that, that's one, but GAD, WDD. But if you have a tensor like this, you can't square it because you can't contract. There's no way you can contract the indices consistently. But if you have a way of raising and lowering indices, then you can turn it into an operator like this, a mixed tensor, and then you can square it, and you get G A B or W A B W B C is equal to. In the same way, you can raise and lower indices on V. And so that's what I mean by saying that it's the square root. Okay. You could write it in different ways, but if you adopt a basis, as you typically do, adopt a basis in which G looks like the identity matrix, then this just looks like, then raising and lowering the indices does nothing to V, and then you're just saying that the matrix that represents, or W, and you're saying the matrix that represents W is just that one which when squared gives you the matrix that represents V. And as always, when you write the square root like this, you mean the positive square roots. So W is the unique solution of this equation, which has WAB as a quadratic form greater than or equal to 0. Okay, so that's the general.
So when V is 1,
So if the two sets of oscillators were not coupled to each other, set 1 and set 2 or whatever, then the off-diagonal elements of V would of course be 0. That's the meaning of not being coupled. It would just be, V would just look like some sort of block matrix like this. with zeros here and zeros here, and so then of course W would have that same form, because you would just separately make the square root of this block and the square root of this block. So these things would be, these would be 0 and these would be 0. So lambda itself would just be the 0. This one, I didn't, I mean, I'll just remind also, I suppose, the upstairs W is defined to be the inverse of the downstairs W. So you would, when you invert W, you would invert this separately, you would invert this separately, again you get zeros here. So both the off diagonal block of W and of W inverse would be 0, and lambda would just be 0. So that would be the extreme case in which lambda was very degenerate. I mean, it had nothing but 0 eigenvectors. So there's nothing wrong with that physically. So what this shows, as I just to repeat something I said last time, is what this shows very nicely is that it's precisely the coupling between the two sets of oscillators that is responsible for the entanglement and the entanglement entropy. The entanglement and therefore the entanglement entropy that measures that amount of entanglement that's present. And then this, then we defined another thing called UN, just for simplicity. So the point is that the entropy is then just a sum over the spectrum, or the sum over the eigenvalues of this lambda matrix. But to write that sum in a convenient form, you can define nu, if I can remember what it was. I think it was this, something like that. Does anyone? Yeah, I can go back and check. I think that was the relation between nu and lambda. And then nu, then in terms of that nu, the entropy was the sum over n of nu sub n lambda, nu sub n minus nu sub n minus 1 log, log of nu sub n minus 1. So that's the whole story that we kind of arrived at. And this, in terms of those fictitious oscillators that we analyzed everything into by diagonalizing W, by diagonalizing, I think, what was it? W tilde, I forget. And there were two other matrices that we diagonalized simultaneously. And in terms of that, we get some sort of fictitious or virtual oscillators. And this nu really represents the mean excitation of that oscillator. So it has a kind of direct physical or intuitive meaning. So that was the...
So yesterday you mentioned that so in our paper we had a similar formula, but in terms of the eigenvalues of this correlation matrix times the C. So what you said is it's not clear what's the connection between that formula and this.
Yeah, the formula looks so close that I'm sure there's a simple connection, but I've never worked it out. So I suggested that it would be a nice exercise. It'll help to understand the whole picture better, to work out explicitly the connection between that formula and this one. So see, this one starts with W, starts with just this G and B. And of course, the setting was a little different. You didn't have a ground state, you had some sort of non-equilibrium state, but in the end you also had a Gaussian density matrix for the oscillators of interest. Bosons, I guess they were of interest. So to make contact with that, what we could do, so here, the answer here is written directly in terms of these coupling constants, G and B, but once you say that you're in the ground state, you can characterize the ground, I mean, once you know what the ground state is, it doesn't matter where it came from, then all the rest is just machinery turning a crank. Once you have the ground state wave function, let's say psi of all the q's, that's the ground state of this whole, these are the QA, capital A, all the q's, so it's psi naught, let's say ground state of Q, both the QA's and the Q alphas. Once you have that ground state, as I just reviewed before in words, then you can compute the entanglement entropy without ever referring again to the underlying dynamics. But the ground state, of course, can be written in terms of G and B. In fact, it's basically just e to the minus square root, and it's just e to the minus w with some factors, qq. I forget exactly what it is. It's something like that. So once you have it, you can get the entropy, but you can also get from it, of course, the correlators. So once you have this ground state, you can compute QA, QB. That's really immediate. It's just W inverse or something. It's just the usual story for any kind of normal distribution, probability distribution. You just square. I mean, you have to square anyway. It comes immediately out. It's immediately connected to this. But there are also correlators QA, PB. And these are hats, meaning operators, and PA and PB. Unless you have all of these, you cannot reconstruct the ground state. But if you have all of these three sets of correlators, then you can reconstruct the ground state or the density matrix. If it's a Gaussian density matrix, then given these three things, you can reconstruct the density matrix. In this case, it's a pure state density matrix as a special case. But anyway, once you have these three sets of correlators, you have everything. So I think what you've done in effect is start with these three sets of correlators and then computed the entropy from that. Or maybe you started with the reduced set of correlators. Maybe you only used, in the end, we only really need the block of the density matrix that refers to the Roman indices, or something like that. So once you have these, of course, it's a triviality to get them just for the Roman indices. You just specialize the Roman indices, specialize the indices to Roman indices. Once you have those, and here, and here, then you have all the information you need, precisely because it is still a Gaussian density matrix. So just in terms of the Roman variables, the retained oscillators, it's still a Gaussian density matrix. So the special property that a Gaussian has is that the endpoint functions, that is all the correlators, are written in a simple way in terms of the two-point correlators. That's what people do in cosmology when they're looking for non-Gaussian energy. In this cosmic microwave background, that's what they look for. They look for a three-point correlator that's non-zero. The Gaussian state, the odd correlators are all zero, assuming that the mean values are zero. And then furthermore, the quartic ones should be written in a very simple way, Wick's rule, in terms of this two-point ones, the quadratic ones, and so on. So once you know the quadratic, if it's a Gaussian state, once you know the two-point functions, you know everything, all the correlators, and therefore you can reconstruct the full density matrix. So it must be possible to rewrite the entropy in terms of these things, and that's what you've done in your own way in the paper. That's what I was also in the paper of mine that I referred to. Something like that is also done, and the formula that I got, I forgot. I think both of our formulas looked almost the same. They both looked basically like this. So it must be possible to start with the correlators, use that other machinery, produce the entropy, and show that in fact it takes this form. And that's what I was proposing as a last exercise to fill in all the missing parts of the big picture.
Yes, I have a question from last week. So last week you said that it's possible to write a reduced density matrix in terms like a thermostat in terms of a modular Hamiltonian.
In terms of what Hamilton? Modular?
Yeah. So I'm saying, is it always possible to do that?
No, it's not always possible to do that, but it's generically possible to do that. So, given an arbitrary density matrix, suppose I would like to write it as a thermal state. Of course, you have to, when I say you could write it as a thermal state, I meant you with respect to some Hamiltonian. So not the Hamiltonian that you may think is the right one, but some fictitious Hamiltonian. That's this modular Hamiltonian. So we're really asking, given this density operator, we're asking, can we find some h such that rho hat takes the form of e to the minus beta h? And actually, of course, it's obvious beta is completely up to you. If you can do it for one beta, you can do it for any other just by rescaling h. So we really don't have to worry about beta. So we're really just asking, can we write rho hat in this form, 1 over partition function times e to the minus, should have a minus there, e to the minus beta h. And that's clearly true if and only if, I mean, if this is true and we take the log of both sides, this is telling us that log of rho hat is minus log of z, which is just a constant minus the operator. I put beta back, beta h hat. So where this is chosen in such a way that so that the trace, we want that the trace of rho hat, if we want, that determines the value of z. So the real question is just, can I take the log of rho hat? And that's true if when can you take the log of a number? The rho hat is a positive, always for a density matrix, it's a non-negative operator. And so when can you take to take the log of it is basically, if you think what it would mean to do it, to actually do such a calculation, you'd probably do it by diagonalizing rho hat and then taking the log of each eigenvalue. The eigenvalues will all be non-negative numbers, so the question is, when do they have logs? And a non-negative number has a well-defined logarithm if and only if it's not zero, right? So if rho has no kernel, if it has no zero eigenvector, zero modes, then you can do it. If it has it, then you cannot. So basically, that's the thing. So this works if and only if the kernel of rho hat is zero. And that's always, a thermal state always has that nature, its kernel is zero, because it's written like this. So e to anything can never be zero. So that's all it meant. So when I said generically you could do it, I was just saying, well, generically you don't have any zero eigenvectors. Whatever that generically means. Okay, so that, let's see how far we can get now. So, but I'm hoping to finish, which I'm hoping to be able to finish today. So I'm going to, until now I tried to do everything very carefully, not leaving any steps out. I'm going to be a little less complete now, and maybe much less near the end, depending on if it seems like time is running out. But what I want to do is discuss the application of all this to field theory, a free field theory, where the two sets of oscillators will now correspond to two space-time regions, or in fact, the way I'm going to set it up, just two spatial regions at a moment in time. And the main things I want to convey are, first of all, so now we want to apply to field theory. So now we're in a continuum, because space is continuous, space-time is continuous, so now we have an infinite number of oscillators to deal with. If you think of a free field as say a scalar field, as a collection of oscillators, which I'll be doing a scalar field. And the three things I want to get out, first of all, convey is the need for a cutoff. That's a very rough heuristic argument why we have to have a cutoff. Second of all, given that there is a cutoff, so that the point, I mean, is that if you don't have a cutoff, the entropy will turn out to be infinite, the entanglement entropy. So if we do have a cutoff, then it will be meaningful to talk about its dependence on things. And in fact, we'll see that it's proportional to the area of the bounding, the surface that divides the two regions from each other, as long as the scale of that separating surface is much greater than the scale, than the cutoff length associated with the cutoff. And then finally, I want to go through and get the explicit formula. So this part and this part are heuristic. But then we have this exact formula, so I want to get the explicit formula for a half space. And there's still, as I referred to once or twice before, there are still some the calculation has never been completed fully. So it makes an interesting mathematical physics problem to complete it and get the exact dependence of the entanglement entropy on the cutoff. That is, basically it's the coefficient of the area. So an area law means that S is some constant times the area, and this constant depends on the cutoff somehow. In fact, the explicit dependence in 3 dimensions, this is the 3 plus 1 dimensions. If L is the cutoff scale, then the entropy is given by the area in units of L squared, but there's an unknown numerical constant coefficient in it. If this calculation were to be completed, you could get this coefficient. And ultimately that's, I think, a very interesting thing to do, because this coefficient is telling you something about the deeper theory that's underlying semi-classical gravity. I mean, I'm not actually claiming that the way that I'll introduce the cutoff is a fundamental way, but but if we did introduce the cutoff in a fundamental way, that if we could relate it to some fundamental space-temporal discreteness that underlies everything, then you would get direct information on the relation of that discreteness scale to the entropy. And since we know the coefficient for the entropy, we would get direct information on the actual scale at which the fundamental space-time discreteness sets in. We sort of expect that it's an order up to the order unity near the Planck length, but a calculation like this done in the more fundamental theory will give you the exact value of that.
Isn't the cutoff supposed to be arbitrary? So why is that going to be? If I rescale the cutoff by 5, why won't that number change?
If you rescale the cutoff here,
Yeah.
then C will have to change to compensate. Yeah.
So then it's
So I'm saying the cutoff is not. I'm saying, well, now it's all conjecture, but my feeling is that there is a fundamental cutoff in the world, and so if there is a fundamental cutoff, then knowing the value of C becomes important because it gives you direct information on the magnitude of that cutoff. So it's true that people who do this a lot, they don't care. They're only interested in what they call universal results that are independent of the value of the cutoff. And so in this case, you may look for subleading terms like log of some multiplying log of A over L. And then that coefficient here, let's call it D, whatever. That can be universal, even though this is not universal. And since it's universal, it gives you an interesting kind of handle on the field theory. But what it precisely does not do is give you a direct connection with the underlying theory. So my analogy for this is like kinetic theory, where if you describe a gas like the air in this room, you have the speed of, the basic parameters would be some sort of diffusion constant and some sort of speed of sound and maybe a few other instead of diffusion constant, let's say, you could talk about the viscosity of the air, and you could talk about the speed of sound. Those, from the point of view of the continuum theory, if we treat the air as a continuum, they're just numbers. They're not universal. They have no, you can't compute them a priori